let's talk about circuit analysis in the S domain. So just to make sure we are all effectively on the same page, when I'm talking about analysis in the S domain, what I mean very specifically there is we are going to use the Laplace transform to go from the time domain into the S domain, where S is our Laplacian variable. Okay. So let's take a couple of moments here, kind of like what we did back when we were kicking off frequency domain or steady state sinusoidal circuit analysis, and figure out how our circuit elements are going to behave in the S domain. And so let's start with the simple case for, that is not an F, goodness gracious. So for a resistor R, we know that in the time domain, we have the relationship V of t is equal to I of t times our resistor value R. So if we took the Laplace transform of both sides, the Laplace transform of V of t would have to be equal to the Laplace transform of, I'm just going to move this R over to the other side, and we would have I of t. The Laplace transform of V of t would simply be some voltage in the S domain. Since R is a constant, we could move it outside of our Laplace transform operation, and now we'll have the Laplace transform of our current waveform I in the S domain, so that once again, Ohm's law is exactly equal to Ohm's law. One of the great things about circuits is that Ohm's law always just looks like Ohm's law. Nothing remotely fancy at all about it. So now let's look at an inductor, right? So for an inductor, L, so let me put, so this will be the Laplace domain thing here, or the S domain. I guess I'll put it as SD. So in the time domain, we know that the voltage drop across an inductor is equal to L times the derivative of our current. So if I take the Laplace transform of both sides of this thing, what I'm going to wind up getting is the Laplace transform of V of t, once again, will be equal to the Laplace transform of L di by dt. So in the S domain, we'll have some voltage as a function of S. And then anybody remember what my derivative property, the time derivative property of the Laplace transform looks like? It's on the table that I gave you guys for what it's worth. If I'm remembering correctly, and there's every opportunity that I'm not, it should just be the Laplace transform of our current I multiplied by S, and then we subtract our initial condition, if I'm remembering that correctly. So that would look like, if I pull L out as a common or constant term, we would have L times S of I of S minus I at 0 minus. And then if we wanted to, we could redistribute through that L. So let's think about this really quickly here. Okay. So I have S times L times current. So we talked much earlier on when we were defining what the Laplace transform and all of that kind of stuff was, and particularly what S was, our complex frequency. And I said that the imaginary part of our complex frequency, J omega, is the frequency that we're used to in our steady state sinusoidal analysis, okay? So if we just think of this S as what's replacing J omega, what we have here kind of is J omega L times I. So what's that J omega L thing? Or that S times L thing? That is our impedance in the S domain. And then we have this thing over here. So what should L times current look like? Let's think about our units here. So inductance is measured in henries, where a henry is a volt second per ampere. So if we multiply volt seconds per ampere times current, we get something in volt seconds. So what I'm going to do is going to maybe seem a little bit odd, but I'm going to come up with an equivalent circuit for this thing, okay? That's going to have an impedance, and it's going to be in series with a source, okay? So my impedance, like I've talked about, is just going to be S times L. And then I'm also going to have a source that is just L times I naught. And I'm going to choose to represent that by a voltage source because it's much closer to voltage than it is current because its units are volt seconds, okay? So in the S domain, our inductance L is going to be replaced by an impedance SL that is connected in series with a voltage source. And because the voltage is negative, because there's a negative sign right here, I'm going to put the negative polarity terminal on the left, the positive polarity terminal on the right. And so this is going to be just L times our inductor current at 0 minus. And I'm going to define the voltage drop across this thing, positive polarity on the left, as V of S. And I'm going to define the current flowing through this thing, so flowing into the positive polarity terminal, as I of S. So I just want to make sure that you guys understand why this voltage and this voltage have opposite polarities. And it's all because of that negative sign there from the time differentiation property of the Laplace transform. Okay, I'm going to put kind of a line right here, because while this is perfectly true, this represents a practical voltage source. So we could actually perform a source transformation on this thing to get a practical current source representation. And then whenever we're using this model in a circuit that we analyze in the S domain, we then have the option of using the practical voltage source model or the practical current source model. And which one we use just depends on which one's going to make the circuit analysis easier, okay? So between that exact same set of terminals, instead of having an impedance in series with a voltage source, I could instead have an impedance in parallel with a current source. So here's my impedance. There's SL. I'm going to put the positive polarity terminal of V of S on the left-hand side, the negative polarity terminal on the right-hand side, so that it's just matching the polarity that I have down here. For my current source, I'm going to choose to put it down here, and my direction is to the right because the positive polarity terminal of the voltage source that I'm transforming is on the right. And then according to the rules for source transformation, I should just take this voltage L times IL at 0 minus and divide it by this impedance. So the L's are going to cancel each other out, and what I'll have is IL at 0 minus divided by S. And then my current is what's flowing into the positive polarity term. So these are two different S domain models that are electrically equivalent to each other that we can choose between whenever we are representing some inductance in the S domain. It should be fairly obvious, but if our inductor current does not, or a better way to put this was, if our inductor doesn't have any stored energy at t is equal to 0 minus, then IL at 0 minus would be 0, which means this thing right here would look like a short circuit, meaning we would only have an impedance SL like we're used to. Similarly, IL at 0 minus over S, so that would be a current of 0 or an open circuit, which means all we'd have is our impedance SL. So these match what we are expecting in, so we should get effectively just the complete steady state response out of these things if we don't have any stored energy messing anything up. Okay. So any questions about these inductor models before we move on to capacitor? All right. So for a capacitor, let's come down here. C, we know that in the time domain, the current flowing through our capacitor is equal to C times the derivative of the voltage drop across the capacitor. And so taking the Laplace transform of both sides, we have L of I of t is going to be equal to the Laplace transform of C dV by dt. And so in the S domain, this is going to look like I of S is equal to C times S V of S minus V at 0 minus. So looking at things here, we have I is equal to essentially J omega C. So rearranging that, we would have the impedance of our capacitor as per usual, where that impedance is going to be 1 over SC. And then we have capacitance times voltage. Well, capacitance is measured in farads, where a farad is an amp second per volt. So amp second per volt multiplied by volts gives us amp seconds. So what we should see is a capacitor in parallel with a current source, and then we could transform that, if we were inclined to, into some capacitive impedance in series with a voltage source, just like we did for the other one. Right? So we would have an impedance of 1 over SC. Actually, crap. Let me do the parallel thing first. So here's our impedance. One over SC. Here's our current source of CVC at 0 minus. And I drew the current source in that particular direction because I'm going to define my voltage V of S here and my current I of S like so. So this negative sign right here tells me that my current source direction should be opposite of my IS direction. Performing a source transformation on this guy gives me 1 over SC in series with a voltage source, where this is just going to be VC at 0 minus divided by S. Here is the positive polarity terminal of my voltage V of S, and then my current I of S is once again flowing into the positive polarity terminal. So depending on what makes my circuit analysis easier, I can either go with current source in parallel with impedance or voltage source in series with impedance. And they are literally just source transformations of each other. All right. So anybody have any questions about this? Yes.
What is that?
So a farad is an amp second per volt. So it's the same thing as a Henry, but you swap voltage and current because it is the electrical dual of a inductor. All right. So let's analyze a problem. So let's say that I have the following circuit. Let me just go to a different page here. So the circuit that we are interested in is a simple parallel RLC circuit. So here is our current IS of T. Here we have our resistor R, our inductance L, and our capacitance C, like so. And here, let's say that R is equal to 125 ohms. L is equal to 0.1 henries. And C is equal to 4 millifarads. So I want us to make some predictions about things here. Okay. Let me tell you guys what IS of T is first before we make our predictions. So IS of T plotted as a function of time for this particular problem is going to be the following waveform. So it's going to be 0 until we hit T is equal to 0. Then it is going to jump up to 6 amperes. It is going to stay 6 amperes until we hit T is equal to 1 second. And then it is going to fall back down to 0. So here's 0, 1, and this is 6 up here. So we could think of IS of t as 6 times U of t minus U of t minus 1 amperes. So we just have an abrupt current pulse. Okay. So if we were interested in determining, let's say, our voltage, V of t in the time domain, I want us to make some predictions about this. Okay. So this circuit is fairly similar to the transient analysis that we did in circuits 2, right? So if we had just abruptly connected a current source and just left it on forever, this would be a total response problem, right? And if we just had this last half of this case, where we had a current source on and then we abruptly turned it off, it would be a natural response problem. But either way, it's something that we've seen before with just a simple parallel RLC circuit. So I think, based on the values of R, L, and C and our knowledge from circuits 2, we can formulate some kind of idea about what this kind of response behavior is going to look like, right? Because we should be able to just use these values to determine if this system represents a critically damped circuit, an overdamped circuit, or an underdamped circuit. And then we're going to find out if the Laplace transform effectively gives us a response that looks something like that. I believe it will, right? So how many of you guys remember how to determine if this system is critically damped, overdamped, or underdamped? I mean, I know a handful of you guys took circuits 2 over the summer, so it should be relatively fresh. Amir?
Square root of L R for one of them?
So omega naught is the square root of 1 over LC. Okay. So the resonant frequency for this circuit is root 1 over LC. So grab a calculator real quick here. So that would be the square root of sorry, I don't use this particular Casio often enough to remember where the square root sign is. There we go. So 1 over, so let's see, 0.1 times 0.004. So that comes out to 50 radians per second. Alpha, if I'm remembering correctly, for a parallel RLC circuit should be 1 over twice RC. So that would be 1 over 2 times 125 times 0.004, which comes out to be 1 Nepper per second. Omega D. So first, since alpha is less than omega naught, this system should have a underdamped response, right? Omega D would be the square root of omega naught squared minus alpha squared. So the square root of 50 squared minus 1 is 7 square root of 51, or 49.989 repeating. So let's call it just 49.99 radians per second. So really close to 50 radians per second. Since omega naught is so much larger, that tends to make sense. Okay. All right, so the first thing that we would need to do for this particular circuit is to convert it into the S domain. So the first question that we need to ask ourselves is, will our inductor or our capacitor have any stored energy at t is equal to 0 minus? No, right? So because we have this unit step response at 0 minus, this current was 0. So no current should be flowing through this inductor because we didn't excite anything. There should be no energy stored. So we're going to get away with just having the impedances, right? So our S domain circuit would simply be our source current Laplace transform connected to our resistor connected to an inductor having an impedance of SL connected to a capacitor having impedance of 1 over SC. And then we would be looking for this voltage in the S domain. Everybody okay with that? All right. So if I were trying to find this voltage, V of S, just using good old conventional circuit analysis techniques, what do you guys think I should do? I may be mistaken, but I believe I heard nodal analysis, and I also believe I heard current division. Hurts my heart that you guys don't see the very obvious solution. I have a current flowing into 3 impedances in parallel, and I'm looking for voltage. Why can't I just use Ohm's law? I times ZEQ. Why can't I do that?
You're so disappointed. Oh, gosh.
I am. I'm rather disappointed in all of you.
The same mesh analysis.
That would actually disappoint me further, yes.
Yeah.
Oh, good God, no. You guys are just trying to put me in more of a shit mood than I'm currently in.
Yeah, it's just a one, like, no, you have to do.
So it's a one equation, one unknown thing, or it's just multiplication. Right? I mean, you guys are absolutely killing me. Okay. So V of S would be nothing more than whatever our Laplace transform of our current is, and we'll get to that in a moment, multiplied by 1 over R plus 1 over SL plus SC over 1, which is just going to look like SC. Right? So we can play around with this thing a little bit. So like I might want to multiply by SL over SL here. I might multiply by R over R here. I might multiply by, let me move this thing out, SRL over SRL, like so, so that I wind up having a common denominator of S times R times L. So let's go a little bit further with this. So we're going to have whatever our Laplace transform of our input signal is. So I have an SL plus an R plus S squared RLC, all divided by SRL. Will come out to be IS of S times SRL over S squared RLC plus, sorry, that shouldn't be R sub L like that. That should be SR times L, S squared RLC, SL plus R. So you may be asking yourself why I bothered to put it in this particular form. Notice that I have a numerator that is polynomial in S of the first order, and then a polynomial in S in the second order in my denominator. So this is something that I could potentially do partial fraction expansion to find the inverse Laplace transform. Now there is a little bit of a problem. Can anybody tell me what that is? For all of our partial fraction expansion stuff that we did, the coefficient on our highest order term in our denominator was always 1. It is no longer 1 right here. So what will we do to get rid of that? Yeah, so divide both the numerator and the denominator by a factor of RLC. And so that's going to give me IS of S times. So that's going to give me an S over C in my numerator, S squared plus S, let me just go ahead and do it like this, times a factor of, let's see, 1 over RC plus a 1 over LC down here. So I believe that I have this in a reasonably good form. So now let's sort out what that whole IS of S is going to be, right? So let's take the Laplace transform of our input signal. Anybody remember how to do that? Okay. So let's do that up here, right? So IS of S would be 6 times the Laplace transform of U of t minus U of t minus 1, right? And I could just pull this as 6 amps out if I were so inclined, but we're probably just going to leave it as 6. So that would be 6 times, so what's the Laplace transform of a unit step function? 1 over S. . what's the Laplace transform of a unit step function time shifted by 1 unit to the right? 1 over s, and then I apply the time shifting theorem that will give me e to the, is it negative s or positive s? Negative s. So minus 1 over s e to the minus s. Okay. So this would give me 6 multiplied by 1 over s minus 1 over s e to the minus s times this thing over here, s over c divided by s squared plus s times 1 over rc plus 1 over lc, like so. Or six s over c. Actually, let me write that as s times a factor of 6 over c divided by s squared plus s times 1 over rc plus 1 over lc minus s times 6 over c s squared plus s 1 over rc plus 1 over lc, and this whole thing multiplied by a factor of e to the negative s. So one of the great things about the Laplace transform, particularly the time shifting property, is that I have this thing and then I have it over here multiplied by e to the minus s. So whatever I get for this thing right here, I can literally just substitute that in and put everywhere I have t, put t to the minus 1 and get the right answer in my inverse Laplace. Toby, what up?
Why would the n equal the numerator not be 1?
Because I wasn't paying enough attention. So actually what I just legitimately wasn't paying enough attention, because you're 100% correct. So 1 over s times that s in the numerator should cancel each other out. What I was thinking about doing was making this an s cubed plus s squared plus s here, but I didn't do that part right either. So either way, I just screwed up the very basic math. So thank you for pointing that out. So that gets rid of that and that. Thank you very much for that, Toby. I appreciate it. And so I think we are in a place where we could do the inverse Laplace transform of this thing, right? So what are our roots of this thing right here, right? So our poles 1 and 2 would be negative b, so that's negative 1 over rc plus or minus the square root of 1 over rc quantity squared minus 4 ac, where a is just 1, all over 2. So if I put this in my calculator, I have negative 1 over R was 125, C was 0.004, plus the square root of 1 over 125 times 0.004 squared minus 4 over, let's see, L was 0.1 times 0.004. Of course, it gives me a complex number in polar form that I don't want. Option rectangular. So I believe this gives me -1 plus or minus 7 the square root of 51. If this guy right here is larger than this guy right here, we get a complex number, right?
Oh,
Did anybody else get that result? Let's start there before I start messing with this too terribly much. No, square root of 51. So let me just 7 root shit. 7 root 51, by the way, is 49.989 repeating. It's that same 49.99 thing we got for omega d earlier. So we could probably more easily call this -1 plus or minus, sorry, that should be J, what we had for omega d. Yes.
I got negative over plus or minus 7, 350.
Let me throw this in my calculator again. Always a possibility I just typed something in wrong. So -1 divided by, so R was 125. Right? Let's go back up here. Times C was 0.004. Okay. Thought I was right. All right, so we have this repeated root. So what does this tell us? What did we do at the end of our last class meeting? This, right? So V of S is going to be some coefficient B1 over S plus 1 plus J omega D plus B1 conjugate over S plus 1 minus J omega D. So I feel like we probably need to figure out what that B1 thing is, and then from there, we're effectively done, right? Because once we know what that B1 thing is, then we can go just to our table. So B1 is found by multiplying S plus 1 plus J omega D times our original function V of S. So just for shits and giggles, that's going to be 6 over C over S plus 1 plus J omega D times S plus 1 minus J omega D. And then we're going to evaluate this guy at S is equal to -1 minus j omega d. This guy right here cancels this guy right there. So let me just do something real quick. So I'm going to store that 7 root 51 in my calculator as A. So I would have 6 over 0.004, right? That's my 6 over C. And then I'm going to have -1 minus alpha A times I plus 1 minus alpha A times I. Sorry, I'm not super used to this calculator. That should check out. I'm making that face because my phase angle came out to be exactly 90 degrees, which I'm not 100% sure on. All right, so let me try this again. 6 divided by 0.004. And then down here, I have what I have stored in my calculator as B plus 1 minus a I. Yep, nope, that's just what I got. Okay, so I got an answer of 15.003 and some change with an angle of 90 degrees. Anybody else get that? Toby, sure. No, so these are complex conjugate poles.
Why are they, where does the conjugate come from in the case of one?
So if we solve for this coefficient B1, where we're effectively, so what we did here for B1 is we multiplied by S plus 1 plus j omega d and evaluate it at whatever makes that thing equal to 0, right? When we solve for our second coefficient, we would do a similar thing, but we would actually multiply by S plus 1 minus j omega d. And we would solve for this at -1 plus j omega d. The number that we get here when we solve for B2 will always be the complex conjugate of B1, so I don't see the point in solving for it.
So as long as the roots are conjugates.
If the roots are conjugates, then the coefficients are conjugates. Yes, Ian.
It is the real part of all sorts of alpha. Or is that just specific to this scenario?
No, so pretty much. So effectively, all I really need this thing is that 15.003 magnitude right there. I also need the phase angle 90 degrees, right? Because we have a Laplace transform, just to refresh you guys's memory. So if I'm not mistaken, let me do this in a different color. So I believe we figured out that for some function of time that was e to the negative at times the cosine of omega t, and I may be misremembering the sign on this phase angle, u of t, it had a Laplace transform of 1/2. Sorry, this should be in the numerator. I believe it was e to the negative j theta over s plus a plus j omega. And then I think this is a plus sign here. I am literally trying to do this from memory, so tell me if I'm mistaken. S plus a minus j omega. Did we do something like that at the end of the class on Friday? I believe so. I'm looking at the person who's literally not taking the class and asking for her opinion, but anybody else who is taking the class can definitely maybe verify this, but I'm 99% sure we had something, if it isn't exactly this, extremely similar to this when we got our distinct complex poles. So I'm not doing the repeated complex conjugate poles. I'm doing the thing that we did before that. Okay, so this is right. So just to be clear here, we have A, we have omega, we have this magnitude 15.003, so we're just going to double that because of this factor of 1/2, and we have our phase angle. So I literally think we are just ready to apply this transform to the results here, and we're good to go. So B of t should be, so 15.003 times 2 should be 30.006. E, so A is 1, so we're going to have to the negative t. And then we will have cosine of omega, which is just that omega d. I'm just going to write it as omega dt here. And then, so when we solve for B1, we got plus 90 degrees. I'm expecting a negative angle, so I'm just going to flip the sign on this guy. U of t. And then I'm just going to tuck in a u of t minus 1 over here, because if we go back to the original thing, we have this identical deal, time shifted by 1 unit to the right. So just taking that in. So does this look like something that we would expect? Now, it does look different, right? So let me refresh your memory on why I say it looks different. Let me scroll way back up here, okay? So up here, we mentioned that we should have an underdamped response, right? When we were in circuits 2, and I know this is just getting messier and messier by the moment, for an underdamped response, we were expecting y of t to be of the form b1 cosine omega dt plus b2 sine omega dt multiplied by e to the negative alpha t plus y at infinity, if my memory serves me correctly, which I'm 99% sure it does. This y at infinity thing is 0 in this case because we turn things off. So why do I have an e to the negative alpha t bit, but why don't I have b1 cosine omega dt plus b2 sine omega dt? Well, these are at the exact same frequency, so I could add those together as a single sinusoid if I were so inclined to do so, right? So B1 angle 0 plus V2 angle negative 90 degrees and just write this as some new magnitude cosine omega dt plus sudden phase angle. That is the form that I actually just got. So we very much see that this is indeed the underdamped response that we were expecting based on our prior knowledge. Now, I would argue that for this particular circuit, it might have actually been faster if we had gone through and just did this as a transient analysis thing. But for the beauty of this technique is that we can apply it to higher order than second order circuits or just RLC circuits, right? So any order of circuit we have, we can apply the Laplace transform technique to analyze our system. I think, Toby, you were raising your hand, maybe?
Can you explain again how the negative 90 came from the block side? I came from that cycling side, but everything.
So based on our identity here, right, this, all I'm just using is this identity. I have e to the minus j theta. If this is a positive number, I'm flipping the sign to get negative theta.
So it's from the S plus A plus.
Yes. Yep, that's it. So applying this identity to just this result right here tells me I need to double my magnitude because I have this factor of 1/2 out in the front. I needed to flip the sign on my angle. And then I can pull from my roots what A and omega are.
So we didn't really need to to get our V2.
Nope, not at all. So if we have B1, we have all the information that we need. And I mean, I can just as easily write this and then put a negative sign there. And who gives a shit, right?
The omega, you get from the omega D from what we're doing.
Yeah, so this is of the form S plus A plus J omega, where this is just the omega D that we had happened to calculate earlier and all of that kind of stuff, right? The 49.989 repeating, or the turns out to be the square root of 2,499, which we could have just been lazy and called it 50 as well, but it's not technically correct. It's just really, really close to correct. And that's just comes out of the fact that when we were looking way back up here, to calculate this omega D, it is the square root of omega naught squared minus alpha squared. And because this guy is 50 times, or excuse me, this guy is 50 times larger than this guy, omega D is going to trend towards just what omega naught was. Okay. And the reason why I use the omega D down here is when I solve for this thing, I could have just left it as 7 root 51 or whatever, but that is literally just the omega D that we found above. And so that was easier to write down over and over again. So I kept that because I'm inherently a lazy man.